Hi everybody, this video is going to be about line integrals. Specifically, we're looking at line integrals on vector fields, meaning that we are interested in looking at paths that go through vector fields. Those are oriented paths, meaning there is a specified direction. It's not just the points that it goes through, but actually what direction it goes through them. And so if we've got some vector field together with some path that moves through its domain, for our line integral, what we'd like is to get positive contributions from places where the vectors in the vector field are generally pointing in the same direction as our motion along our path. And we would expect to get negative contributions from those places where the vectors are generally opposing the direction of our motion along the path, and we would expect no contribution to a line integral at those places where vectors are either zero or perpendicular to our motion along the path. And so if we look at this specific example, we would expect some negative contributions, say, from the left-hand side, where as we see by the arrows, this path is moving from left to right, and over on the left side, the vectors are generally pointing in opposition to the direction we're moving along that path. A little bit further down, there's a place where the vector is perpendicular to that path, and then later, off to the right, we see that the vectors are generally supporting the direction we're moving along the path. So there will be some negative stuff, some zero stuff, some positive stuff, and the line integral is really going to be looking at the net value as we move along that path in terms of the vectors that are along it. Okay, so if we've got some vector field given by some function capital F that assigns to any point in space xy a vector, and we have some oriented path defined by a vector valued function. So you give me some value t, and I'll tell you what vector, the coordinates of the vector, so that points from the origin to a point in space, and the collection of all those points. This gives us a parameterized path, this vector valued function. And hopefully what we're thinking about then is that if we're looking for when things are generally pointing in the same direction, or when they're perpendicular, or when they are opposing each other, we should be thinking about the dot product. And specifically what we can use is the dot product of the vector field at some point along the path with the derivative of that parameterized vector valued function that defines the path. Because remember, that derivative is going to show me what the direction of motion is at any particular point along the path, and if we dot that with the vector field, it tells us whether we're getting things generally in the same direction or generally in opposing directions. So again, here's the picture. We've got some vector field, we've got our path, and at some particular point, the purple vector here is r prime, which shows me what direction I'm moving at the instant where we are at the tail of that vector. So if we dot that with the vector field at that point, that gives us some indication of what we're looking for. So if the dot product tells us at any point whether or not things are in the same direction and by how much, or in opposing directions or by how much, or perpendicular, or the vector field is zero, for instance, then all we really need to do, if that's parameterized in terms of t, if I can figure out that value at any value of t, then we just need to add those up for all the different values of t along our path. So we'll start at some starting value t for our starting point of our path, and end at some ending value, another ending value for t at the ending point of our path. And if we integrate that dot product across all those t values, that'll give us what we're going to call a line integral. Another notation you'll see, you can think of r prime t dt as dr, d the vector valued function r. You can see that from a healthy abusive notation. If you write down r prime as dr dt, then this will symbolically at least make sense. And so calling that dr, you'll often see the line integral written this way, whereas it's just f dot dr, and that's over c, where c is some path, some oriented path described by the vector valued function r. Okay, so let's look at an example. Given the vector valued function which describes our oriented path with x component 2t and y component 3 minus t, so given some value of the parameter t, that tells me what my x and y are that are on the path. And we want to go from the point 0, 3 to the point 8, negative 1. And the vector field we're interested in integrating through is, integrating over is 3x and then x squared plus y. So how can we handle this? Well, first we need to figure out what the value of the vector field is at all the different points in terms of our parameter t. And so f of r, and really that's just a shorthand, what we're thinking about is r tells me the points x and y that are on the path, and so x is 2t and y is 3 minus t. So plugging that in to f, I get f as a function of the parameter t. I get those vectors at the points along the path. And then we need to make sure we know what direction we're headed at every point based on our parameter t. And so we're just looking at the derivative. So it's, again, it's the component-wise derivative, the derivative of the x component, and then the derivative of the y component. And then setting up our integral. The most important thing that we have to pay attention to at this point, then, we can take f dot dr, or f dot r prime, and integrate with respect to t. The bounds are important. What bounds for t are we going to use if we want to start at the point 0, 3 and end at the point 8, negative 1? Well, when t is 0, according to that function r, we are at the point 0, 3, and we get to the point 8, negative 1 when t is 4. And so that's what we'll integrate. We'll take f dot r prime and integrate that with respect to t from t value 0 to t value 4. And so you, I'm sure, can deal with this integral. You could have dealt with this integral in your previous calculus class easily. So take a moment to figure out what you get. And if I didn't make any mistakes, we get this. And that being a positive number means the vector field was more often in support of the direction we were moving along our path. What would be the case if the vector field was more often than not in opposition, or more strongly in opposition in total to the direction we were moving along our path? What would we get for the integral, for the line integral in that case? So this is the basics of line integrals on vector fields, and we'll talk a bit more about this in class. I'll see you then.